It's fine. Just a second.
Yeah, but I don't need like, maybe we can just talk later.
To know what you actually want.
Oh, mostly an opinion. I haven't, I'll go through the papers too.
Okay, sure. We can sit down.
Yeah. Okay, that's one shoot. I'm glad she's taking the initiative to come over and show.
Well, I mean, it's indicative of the fact that
Oh, well. Yeah.
it's nice to talk.
Yeah. But I've also given a lot more thought about, you know, so anyways,
Should we go
today and
through-
tomorrow, yeah.
Yeah. I don't think it's wrong. I don't think it's
Okay.
my very first. I would like to read it.
Okay.
Yeah, I'll get started. So continuing from the last lecture, I'll discuss numerical dispersion and numerical stability issue. So you know, in vacuum, the dispersion relationship is very simple. It is omega equals ck, right? So in vacuum. Maxwell's equations. So dispersion relation is simply the relationship between frequency omega and the wave vector k. So is there any person who doesn't know this relationship? So this is simply derived from Maxwell's equations. And however, the FDTD optic equations we learned last time depict something different. So FDTD optic equation, which is different from Maxwell's equations. So it dictates something called numerical dispersion relation. So for 1D cases, it looks like dispersion relation is, as I said, simply the relationship between the frequency omega and the wave vector k. And numerical dispersion relation is also the frequency omega and the wave vector k. So currently it is written in implicit form, but still it dictates the relationship between omega and k, right? So we can derive this numerical dispersion relation from the update equation, but I wouldn't go through the details. It is very standard procedure in any FDTD books. So if you are interested, you can look for the equations in the books. But I'd like to focus more about something practical, some practical issues. So if you look at this equation, you realize that for real omega and k, so the left-hand side quantity and the quantity within the brackets is actually between 0 and 2, right? Because cosine is between -1 and 1. That means if the factor c delta t over delta x is greater than 1, then for some real k, there's no corresponding real omega, because if this is greater than 1, for some k, especially the k that makes this quantity equals 2, the right-hand side quantity becomes greater than 2. But the left-hand side quantity should be below 2. So there's no omega that satisfies the equality. So again, as I said, if k is, for example, pi over 2 delta x, then the quantity within the bracket becomes 2, right? So then the right-hand side becomes greater than 2, and there's no omega that makes the equality false. If this happens, the update equations becomes unstable. I'll show what that means shortly. Therefore, you cannot choose delta x and delta t independently. Delta x and delta t should satisfy. This condition. It is called stability condition.
So if this k equals delta x pi over delta x, not 2 times delta x. Because
Oh yeah, sorry. Yeah. Thank you. I'll show you what happens if the stability condition is not satisfied.
May I ask a question?
Sure.
Do we also have the same problem when there is an imaginary k, for instance? You don't have cosine hyperbolic function. It can be larger than 1.
That is true, but what FDTD update equation solves is, for example, when you have an initial distribution of E field, it can be decomposed into Fourier series, for example, and that has real k. So and we see how this each Fourier component with real k evolves in time. So that is actually a very good question. We assume k should be always real, and find the condition where omega is not real. Actually very simple MATLAB script that solves the 1D Maxwell equations. And here I have defined a parameter called Cmax. That is the ratio between C delta t and delta x. So if I set this to 0.99, then it is less than 1, so it satisfies the stability condition. And this is what happens. So what it solves is that so when you have the initial E field distribution that has the triangular shape, and let it go, then it propagates in both directions. But you can see that it propagates without any problem. And if you increase this to 1, if you increase the C delta t over delta x to 1, you still see that there's no problem. Now, if you increase this to 1.01, then you see something here, right?
Okay.
choose more slightly larger value, 0.02, that it increases like crazy. Okay.
What about 2?
2? I haven't even done that, but let me. Yeah.
Probably.
Yeah. So that's what happens when the stability condition is not satisfied. Usually you don't have to worry too much about this because the commercial software for any FDTD program usually choose that value such that it satisfies the stability condition. So for example, in numerical, by default.
Is there any reason for there to be 2 lines and not 3 or 4 or 1? Like, is there any reason that it's that close to 1 but not any closer or further away from 1?
Small,
Small?
we can have
Yeah,
a larger, smaller.
I'll show you why that's the reason and why we choose the value close to 1. So I'll call this equation 1. And now we'll look into more details about the numerical dispersion. So up until now we looked into numerical stability issue, but we'll look into numerical dispersion in more details by solving 1 for k. We get okay. So this result says that the numerical phase velocity is omega over k, which is omega over 1 over x cosine. So I simply substituted this previous result into k here. So on the other hand, physical phase velocity is just constant, right? In vacuum. This comes from omega equals ck. So the bottom line is that for given delta t and delta x, if you use update equation instead of the Maxwell's equation, your phase velocity is not constant, even if the medium is homogeneous. So given delta x and delta t, the numerical phase velocity is a function of so what that means? That means wave packets get broadened wave packets broaden as they profile.
I think as long as k delta x or omega delta t is far less than 1, they
Yes.
should be okay.
Right.
Because-
Yeah. I'll tell you about that later. Another consequence is that even for a constant frequency omega, if delta x changes, with position, then so if delta x is a function of position, then even for constant frequency, the numerical phase velocity changes as a function of position. So what I mean by delta x changing with position is something like this. So delta x doesn't have to be constant. It can change with position. So for example, if your scattering event is occurring in this dense area, by using this binary grid around the scatter, you can resolve the phenomenon much better. So delta S doesn't have to be constant. Then, even if this entire space is filled with vacuum, and you are shining monochromatic wave from left to right, because delta S changes, this numerical phase velocity changes. So as a result, stress reflection so whenever the phase velocity changes, there occurs reflection, right? So the reason the light bends when it transmits from the air to water is because the phase velocity in water and air are different, right? So exactly the same thing happens, and I'll show you again. How it happens. This is actually numerical, and this is very simple 2D system where you have PML here and PML here, and the central region is filled with air. And I display the grid. The mesh, and if I enlarge this region, you can see that the grid spacing changes, right? So this region has very dense grid, and this region has coarse grid. And I have a plane wave going up, and the result that I generated out of that setup goes up, you see faint waves going down, right? I'll play this again. So wave goes up, and faint waves goes down. So that happens because of the spurious reflection due to grid spacing changes. So if you use the constant grid, then this kind of phenomenon doesn't happen.